Good afternoon, everyone. Welcome to the MD2K's webinar series. Today, we have a theme that is particularly relevant in the context of all the security hacks that we have been reading about in the national media. To speak to us today, we have Isaac Potoczny-Jones, who is the founder of Tozny, to speak to us about security and privacy issues as it relates particularly to mHealth. At the end of Isaac's talk, we will have a brief opportunity to pose any questions to him. And I've also alerted him that we have a very geographically dispersed audience. So let's invite Isaac. Isaac, you want to take over?
Thank you so much, Vivek. Thank you for the introduction, and thanks a lot to Barb for getting all of this webinar set up, and to the audience today for attending. Really appreciate your time today. I'm really excited to talk to you and address you about privacy, security, and trust, or as I like to think about it, doing more with data by doing right with data. There's some of my contact information in the lower right-hand corner if you want to drop me a line now or in the future. A little bit about what we're going to cover today. We'll just do a quick introduction of me and my company, talk about how we think about privacy and security for innovation and how that relates to my assumption about how I think folks who are listening to this seminar think about mHealth. And then I'll shift into security and privacy challenges in mHealth, specifically in IoT in general. Then go into our project with NIST, the goals of our project, and how to join in the pilot if that sounds of interest to you. And go through a scenario for how to build security and privacy in as a foundation for your work in technology. On to the introductions. So we're actually founded to improve privacy and security. We have a collaboration with NIST, the National Institute of Standards and Technologies, who promotes best practices for security and privacy. They're doing a lot of work right now in defining security and privacy strategy and standards, primarily for the federal government, but also across commercial industry where they have a very positive influence. As part of our work, we have the scope to include pilot participants in our project. So if the things we talk about today sound interesting, it may be useful to work together because we're looking for early feedback and metrics to improve our products and to help understand how security and privacy can improve the situation for your users. A little bit about us again, we are security and privacy experts. We have been founded by collaboration with a company called Galois, which is here in Portland, Oregon, which is where I'm speaking to you from today. Galois was founded in 1999 and does research and development for primarily the US federal government, these agencies that care a lot about cybersecurity. And so we've always been doing defensive cybersecurity for these agencies since our founding. I've been working at Galois since 2004, worked there for 10 years, and then spun off Tozny in collaboration with Galois to take the research and development we were doing and transition it into practice. That path may sound familiar to many of you who are probably working or have worked in research environments and are interested in transitioning that work into practice. So we probably have a lot in common in that area. So let's dive into the way we think about privacy and security in mHealth. I think it's really clear that the potential in mHealth is really enormous. It means having really unprecedented and personal access to people's lives, being able to measure and respond to virtually every aspect of an individual. And as part of that, we will probably transfer personal and private information to central processing points or even distributed processing points. And we would like to get access to that data for unanticipated new analyses that we may like to try in the future. But if we don't tackle privacy, there's the risk that users just won't share the things they could share. We may expose them to unanticipated risk, and quite frankly, we might just be creepy. Some of the things we'd like to be able to do with data are just a little scary if we don't do a good job with security and privacy. And our view generally, probably similar to yours, is that innovation is a very powerful force for good. I'll talk about risk here today, but I don't want that to get overwhelmed by the positive side of things, which I'm sure most of you are focused on. Technology can unlock completely new ways to manage health. Data can be real-time. It can be much more reliable than, for instance, self-reported information that people provide. The analyses that you guys are building can be much more innovative and insightful than what's possible today, and the innovations can be much more immediate and much more personal than what's available today, with very brief and periodic visits to a healthcare professional. So that's my kind of assumption of your view of the world. Our view of the world is very similar in many ways. We also think innovation is super important and that it can be a very powerful force for good. We think that work in innovation is desperately needed to make privacy and security really usable. And that goes for those who are developing and deploying software, because we think far too often security, cryptography, and privacy tools have just not really been made available to software developers. Similarly, for end users, privacy can be tangible and manageable for those users. So in the end, we're really a team of crypto nerds trying to make something great in support of organizations like you. Now, I'll constantly make a little bit of a distinction between security and privacy, and it may be worth mentioning why I make that distinction. The way I think about it, and the way many do, is that secure data, or you can say that data is secure if it's only accessible by authorized parties. And that's one part of security. That's the confidentiality part of security. Now, privacy is slightly different. If data is private, that means that the user has a meaningful say about who those authorized parties are. So that's a slight difference. Security is about making sure it's only the authorized parties, and privacy is largely about having a say in who those authorized parties are. But of course, you actually can't really have privacy without good security. And as I think if anybody who follows the news knows, data leaks are violating the privacy of hundreds of millions of people every year. All kinds of information has been spilled about our daily lives. And on the flip side of that, a secure system, a system that is otherwise secure, can have bad privacy policies. So that goes into things like re-identification attacks, where you can analyze data that you thought was not identifying for an individual and yet actually identify those individuals. Third-party access to data that's unanticipated by the user or not really, or something that the user is really just not aligned with sharing. Lack of transparency for the user in how data is shared, and no accountability in organizations who are collecting and sharing data. So those challenges are separate and distinct from the security challenges of kind of keeping the bad guys out. You can have a very secure system that has bad privacy properties. And sometimes it's worth mentioning, does privacy really matter? And when people ask me that question, I pose a set of kind of counter questions here. Maybe I won't go through all of them, but it's do you do anything that someone would ever disapprove of? Or do you believe anything that someone else would disagree with? Or do you have anything that someone else would want, etc.? And if the answer to any of these questions is yes, then who is that someone that might disagree with you or disapprove of you? And do they have influence, control, or power over you as a user in your daily life? If they're your boss, your insurance agency, someone trying to sell you something. If the answer is yes, then privacy matters. And I would say for almost all of us, privacy does matter. And again, why this is important for mHealth will become clear, I think, in a moment. But the influence and the way mHealth can permeate our daily lives can have a very disproportionate effect on privacy. But as a security and privacy professional, I recognize and have to recognize privacy can get in the way, and it does get in the way. Same thing with security. We have to acknowledge that if data were freely available and you didn't have to worry about privacy protection or consent, then you could do more with that data. You could probably get better health outcomes with data if you didn't have to worry about privacy. And so I have that picture on the left of a gate over a road that the tracks in the snow kind of show people have just gone and driven around that gate because the gate's ineffective and it's just in the way of things, getting things done. And I have to acknowledge that's sometimes the case. But on the right-hand side, I say, privacy does matter. So why don't we start to think about it as a foundation that you can build good things on top of and not as a gate, not as a barrier that's in your way. And as a little bit of an example of what I mean by building on it as a foundation, think about when you log into your email and you have an account. This concept of an account is even what I mean by a foundation of privacy. So much of the systems we interact with on a daily basis use this concept of an account, which is really a security and privacy concept that says my data is separate and distinct from other people's data. And computer systems don't, unless you build them in, have this concept of an account, or web systems don't have that concept of an account. So we build it in not just because it's important from a security and privacy perspective, but because it actually helps us reason about how data is handled and managed and gives the users a way of managing that data. So that's what I mean by thinking of it. We tend, especially as end users, we don't think of our accounts, our email accounts, as being a barrier to anybody. We think of it as a way of structuring data. So that's how I like to think about these problems. So let's talk specifically about certain risks and failure modes for mHealth, and particularly how we can learn from the problems that have come before us. So backing up pretty far here, when email was first invented, it had virtually no security. Many of you probably realize this. Everyone knew everyone else, and there was virtually no value in hacking it. This actually persisted for a very long time, probably for 20, 25 years. And you may remember the days, there was a while where spam made email almost unusable. 90% of the mail in your inbox was spam. And that's really was an inflection point for email, where people had to get really, really serious about security, both in the front end and in the back end for how email was managed. And frankly, we've been trying to bolt security onto email for the entire existence of its life. So we still get spam. There are still phishing problems. There are still problems with forged email attacks. And that's because email was never designed to be secure. And we've been trying to improve that situation. And many really, really good approaches to security have been invented in that time. And there are lots of tools in the toolbox. But I have to say, we make the same security mistakes every time a new technology is invented. When we figure out how to attach a car to the internet, like what's happening today, we make the same security mistakes as we did when we invented email. We trust too much. We make technical mistakes, bad encryption, bad login security, and out-of-date software. We make policy mistakes. The systems that work on these pieces of data in the back end kind of trust each other just a little too much. They don't authenticate strongly, and they pass data to parties that don't need access to that data. And we bolt on security after building the system. Privacy mistakes happen too. We don't give good visibility into the handling of data and the sharing of data. We don't give good tools for consent management, and we collect more data than we really should. And I bring this up because IoT and by extension, mHealth. Now, I don't say IoT and mHealth are the same thing, but they inherit many of the same problems because of the way that sensors work. But IoT really stands out because it has very fast growth and it has really abysmal security today in most cases. So let me give a few examples. You probably heard about the smart camera attack, where smart cameras had been used. Actually, there was another instance today, but in mid-October, a massive cyber attack took out a big chunk of the internet. And this was what's called a distributed denial of service attack, where many devices, many computers in people's homes and businesses were taken over by the attackers and used to target critical infrastructure for the internet. And those quote unquote computers were really just smart cameras. But smart cameras are really just computers. They were installed with default passwords that the adversaries used against those systems. So a lesson here is that these kind of security shortcuts may seem like a reasonable compromise at the time, but a lot of small devices can add up to a really huge problem. And in this case, not just for the end users and manufacturers of the systems, but really for the entire internet. Here's another example of fitness trackers, which are wonderful and very, very popular nowadays. I'm sure many of you are thinking about how you can use fitness trackers or the data from fitness trackers in your analyses of the user's health. I'm very much a proponent of that. And there's this great study a recent study by this organization, Open Effect. The study is called Every Step You Fake, which is cute. It demonstrates, among other studies, that there are significant security challenges in many or most of the fitness trackers that are available today. And they point out very strongly, some are better than others, and notably Apple's fitness tracker is actually quite good for security, according to this organization. But most of them have some critical issue. And so this diagram below is mine to try to explain various steps in the process, which apply not just to fitness trackers, but to many types of aggregate sensors that can be used to measure and have an effect on the user's life and behavior. So starting at the lower left-hand corner, we have a fitness tracker with some kind of wireless, probably Bluetooth interface. Other protocols here are Zigbee and Z-Wave, not so much with fitness trackers, but with other devices. And in many cases, not in every case, this data is not encrypted when sent to the mobile device or to the user's hub. Now, I should point out, I'm not sure that any single system has all of these problems. These are illustrative problems that, as aggregate, many of the systems have. Along with that first step of the product of the pipeline here, where the data is not encrypted when it's sent to the mobile, that means this private health information, if it is private health information, is being broadcast to anyone with a receiver who has bothered to try to intercept that data. Similarly, along the same lines, a malicious user or adversary could, in many cases, put fake data into the system. And this may or may not really be a problem, depending on what the data is and what you're trying to accomplish. But if there is an incentive for a user, for insurance reasons or any other reasons, to provide fake data, many of these systems really don't protect against that kind of behavior. They're really not anticipating it as a problem. But we do have to anticipate it as a problem if there is an incentive. Once the data gets to the hub, in most cases, people do a decent job of uploading it to the cloud, which I've described as the fitness server in this case. But in some instances, actually, even this step is not encrypted. So anyone on the network or who could listen to the wireless on this mobile, the data was sent along with identifying information about the user, which was not there probably way back here, was sent to the server. Once on the server, many servers, this is very clear from other studies by HP and others, demonstrate that these servers have typical web vulnerabilities. Your cross-site scripting, your SQL injection, and denial of service attacks that put the same data at risk. And then from a privacy perspective, as the data gets shared out to third parties, it's shared, sold, and aggregated in ways that the user has no visibility or control over. So this is, again, each of these steps are examples of what can go wrong, and I'm not accusing any single system of having all of these problems, but these are the kinds of things at every point of the way that we have to watch out for. Some of you may have also heard in the news about a certain smart TV manufacturer. Now, they have a nice, convenient feature with their smart TVs where you can give it commands using your voice because they have a microphone in the TV or in the remote control. I mention this because a microphone in the home or other sensors, video cameras, motion sensors in the home can provide really valuable and insightful health information. In this case, it's the same kind of information as being used for entertainment to control a TV, but the privacy challenges for something like a smart TV can be illustrative of how we can structure systems for healthcare that do a better job here. The somewhat amusing text in their very long privacy policy said, please be aware that if your spoken words include personal or other sensitive information, that information will be among the data captured and transmitted to a third party. Basically, their privacy policy stated that anything you say may be transmitted to a third party. And although their privacy policy was actually quite long and detailed, it didn't really indicate what data the television or remote control would hear, what it would record, what it would transmit, and who it would transmit it to. The purpose was not to listen to everything the user was saying. The purpose was just to listen to certain commands to change the channel, for instance. But we don't know what the effect of the microphone and cloud processing of the user's spoken voice actually is, because although the privacy policy was long, it omitted that critical information about how the data was going to be used. So the privacy warning ended up being a bit of a liability in itself, because it really alarmed people. It caused a lot of bad press. And it's really important to, as a lesson learned, that these smart technologies sense our very private lives. And we can't just kind of embed something in the privacy policy basically saying that users shouldn't have private lives if they don't want us to overhear their private lives. We have to really admit to ourselves we're going to be detecting and sensing the user's private lives, and we have to figure out how best to deal with that. Also on the privacy side of things, this is a problem I want to walk through with large data sets. And pose the question, is there really any such thing as de-identification, which is identifying information out of a data set and processing it? It's a good step. It's an important step to segregate that information, but there are limitations and challenges to keep in mind. So the example here is one of about 5 or 10 examples that we have up on our blog if you guys want to read more about this type of challenge. This was a few years ago. I believe maybe it was 2013. The New York taxi cabs had an open data set that provided pickup location, drop-off location, times, and I believe fare and tip amounts. So the data set didn't include the passenger's name and address or the driver's name and address, but maybe you can see where this is going. The researchers actually trolled through a ton of photos of celebrities to find celebrities getting into or getting out of cabs, found the time and date of when they got into and out of cabs, and correlated that with the time and dates of pickup and drop-off locations for these taxi rides. A fairly clever thing, but they learned new things about those celebrities when they analyzed this data set. For instance, they had a photo of their pickup location already that was on the internet, but then combined with the taxi cab data, they found their drop-off location. They found their fare amounts and whether or not they tipped. So this information was not in the public domain before these two data sets were correlated and used to re-identify these users. So the lesson here, especially as data sets get very large, and especially as access to those data sets becomes unfettered, as was the instance here, where these data sets were open to anybody, the data sets can be used to re-identify users. And it's very, very hard to predict what will be identifying information about users and how these correlations could happen. So when it comes to security and privacy, why are mHealth and by extension to some extent IoT different from the way we think about security and privacy with other types of systems? Well, for one, there are possibly many sources of data. We'd like to be able to source data from mobile phones, from sensors in the home, from wearables, and from these analysis engines that try to decide what's happening. Is the user smoking? Has the user had a fall? Is the user likely to have some kind of health problem in the very near future? So just the fact that there are many sources of data, many things we might like to do with the data, make it challenging to control sharing. In many cases, particularly for sensors, these devices are cheap. The batteries, because there's so many devices in a way, the batteries need to last for a very long time. And this actually impacts security in a somewhat surprising way. It impacts the strength of the cryptography that these devices can use, and it impacts whether they can be connected to the network reliably. These two things matter quite a bit, as it turns out. Weaker crypto not only is somewhat easier to attack, which is usually not the problem, it's actually harder to manage keys with weaker crypto. That's symmetric crypto. Another issue is the large scale of these devices. There are many, many devices creating many likely small bits of data. They're distributed by various manufacturers. And so there's a lack of standards in how these devices interact. And again, key distribution becomes extremely complex when you're working with many devices and many manufacturers. In many instances, there's a lack of user interfaces. Some devices have literally no screens and no buttons. They may be standalone sensors. How do you use a knowledge-based factor like a password in a situation where there is no keyboard to type it into? How do you match up a big random number against the trusted source like they use in, if you've ever paired a Bluetooth device, if there's no screen to display that number on? So there's various and inconsistent workarounds for how we deal with a lack of user interface for provisioning and securing these devices. And finally, perhaps one of the most scary and challenging problems is that many of these devices have difficulty getting security updates. For those familiar with security, you may know that most security problems are basically mistakes that programmers like me have made. An error creeps into the code, and over time, those errors get identified by good guys or by bad guys. And so the older things get, the more likely they are to have security problems. So that's why you have to say yes when Adobe or Java say, hey, can I get an upgrade because I have a security patch I want to apply. When you have a system that's disconnected, for instance, it's not on the internet all the time, it's very hard to get those security upgrades. And some types of very critical devices just can't go offline to get the upgrades and reboot themselves. So these systems aren't patched, patches don't get applied, and these systems become vulnerable in the long term. Compounding this problem, in fact, many of these systems use exactly the same software as my laptop or my server use. They use Linux or something along those lines. And so problems get identified in Linux because attackers are going after servers and then get applied to people's Wi-Fi routers, sensors, wristbands, the same exact vulnerabilities. Another complicating factor is that risk is very hard to measure and define for these types of systems. Some devices have very low to moderate risk. You could probably consider many smart home devices or fitness bands or entertainment devices to have relatively low risk for loss of the confidentiality or integrity of the data. On the other hand, many devices are very high risk. They have life and death consequences if the device goes offline, if it's hacked, or if the data is leaked. And that includes medical things as well as vehicles. For instance, some of the attacks we've seen in the news recently. So one of the challenges with these types of systems in a multi-device environment is that the risk aggregates in surprising ways. For instance, a motion sensor that's in my house to turn on my coffee pot when I walk by in the morning has a very low risk profile. If the coffee pot doesn't turn on, that's not that big of a deal most days. But the same motion sensor could actually be in my neighbor's house to call the police if it sees an intruder, or to call a caretaker if it thinks that an elderly patient hasn't gotten up in the morning. So this is the same sensor with the same risk profile, but when the same risk profile when taken on its own, but when combined with the whole context of the system, it actually becomes a very critical device. And so it's very hard to understand how these systems in aggregate behave. The lines between the systems become blurred. For instance, your car entertainment system might not be properly segregated from the brakes of your car. This has been shown to be the case for certain vehicles. And this is true of any complex multi-system device aggregation system today, where it may be the lowest common denominator that causes a security or privacy challenge. So just to summarize the kind of gloom and doom part of the talk, the failure modes, both in the area of privacy and security. I would say privacy, again, I want to emphasize, can we think of it as a foundation on top of which we can build things, not just a barrier that we have to get around. Very similar to smart home and IoT devices, mHealth devices can be very, very invasive in our daily lives. So long, vague privacy notices can be more of a liability than a solution. And the more data we collect, the more difficult it is to stop correlation and re-identification attacks. On the security side, hate to say the same old vulnerabilities are happening in new devices. To summarize again, it can be very difficult to update IoT devices. Many of them have insecure wireless communication, like the old days of Wi-Fi when we were all using very insecure Wi-Fi. They are connected to insecure cloud services, and devices that you deploy one place can compromise the security of other devices nearby or in distant parts of the world. Okay, so shifting gears a bit, I want to talk about our project with NIST, the E3DB. The 3 E's are for end-to-end encrypted database, and it's a type of system called a personal data service. So again, shifting gears, been kind of talking about high-level principles and challenges as sort of an educational discussion. And now I want to shift to talking about specific vulnerabilities and solutions and how we try to address them. And we invite you to work with us or to build systems that use a similar approach to addressing these problems. So here's some questions I'd like you to keep in mind as we go through this. So as a pilot, we're looking for feedback and validation. So if you have the opportunity at the end of the conversation today or offline in email or for a phone call, do you see challenges for your teams in these areas that I'm discussing? And if you do, would a solution like E3DB that I'm going to discuss, would it be valuable for your team? And what requirements would be most important to you for a product like this? What makes it actually practical for you? So diving again into challenges and how we address them, I'm going to talk about particularly data breaches. When the way to read this slide is that for every record in a data breach, this is the average cost per record for that data getting disclosed. You can see in regulated environments like healthcare, the average cost is significantly higher than others. Now, mHealth sometimes may include that same kind of data and sometimes may not include that same kind of data, depending on what's being collected, processed, and analyzed. The point here is to say, how can we make this number better? So if an attacker gets into your system, they can access certain kinds of information, then not other kinds of information. What really moves the needle? And we've developed our system to try to move that needle. So here's another chart from that same study that shows what are the things you can do right that decrease the cost per record, and what are the things that you can do that increase the cost per record of a data breach? So the positive side here is good and the negative side here is bad things. So we're building a technical product. So we said, how can we build a technical solution that changes that problem? So the one thing they point to is extensive use of encryption is one of the best things you can do to reduce the cost of a data breach. On the flip side, extensive cloud migration, moving data into the cloud, is something that makes a data breach more expensive. And third-party involvement in access and control of that data also makes a data breach more expensive. So we're building a solution that uses the tool of extensive use of encryption in the cloud to help with data sharing with third parties. So this is a kind of high-level view of what our product is. And the way to think about it is that it works like a normal database, like a NoSQL database. It's a little bit different if you've ever used a relational database. NoSQL databases are a little bit simpler. Data is encrypted at the endpoint with the key that's known to the parties who control or produce the data. And it's decrypted also at the endpoints by the parties who receive the data. And all the things in between don't get access to the data. So we help you manage the keys so that they're encrypted at the point of origin and decrypted at the point of use. That point of origin could be a website, it could be a mobile app, it could be a sensor or some other information directly from the user. So the idea is, let's get this data encrypted as soon as possible. And I don't just mean encrypted during transit, like with HTTPS or TLS. I mean encrypted for storage. This is really a storage solution. So we encrypt the data early, we transmit it via secure means, and then we store it in its encrypted format so that if any attacker comes and hits any of those intermediate systems, all they get is the encrypted data, and that greatly reduces the risk of such an attack. So one of the problems here is that crypto is actually extremely hard to do right. Many times it looks like you've done it right, but it's hard to tell. Most crypto isn't actually implemented securely. It seems easy because there are support libraries out there, but cryptographic implementations are deceptively complicated and nuanced. Many of these tools make it look like you can check a box and you have transparent encryption, but that actually doesn't necessarily protect against certain types of attacks. It helps if someone steals your laptop, but if someone attacks your laptop remotely or attacks your server remotely, transparent is just as transparent encryption is just as transparent to the bad guy as it is to you. That's not to say there's no value in it. There is extraordinary value in it, but it doesn't necessarily secure the system in the way many people think it is being secured. Similarly, bad key management often undermines good cryptography. When people have done a good job with crypto, I often ask them, okay, now tell me, what are you doing with the keys? And the answer too often is that the keys get stored right next to the encrypted data, which undermines the use of the crypto altogether. So we want to give you a solution, libraries that you can put into your code, and tools that you can use on the client side to encrypt the data as early as possible before it goes onto the cloud at all, and decrypt it as late as possible when it's being processed or shared. So one instance is this picture shows sharing data directly from one user to another in a way that's encrypted all the way through all the intermediaries. You don't have to touch unencrypted data, and we don't have to touch unencrypted data. The end-to-end could be multiple users, or it could be multiple systems within your environment, or it could be with other parties that you're sharing with, which I'll get into in a moment. Here's the challenge with third parties. You often don't control how a third party or even other systems within your network may manage data, but it's impossible on the modern internet to avoid third-party sharing. Many companies send their data to third parties. They encrypt it while it's being sent, but then the third parties side store it into their data silos. And so it's very hard to know what they're doing, whether they're doing the right things with that data, unless you do a security audit. And even then, that's a little challenging. But third-party data breaches still impact your organization. So it's important for you to be aware of what's happening with that data. We recommend kind of flipping that model on its head. Instead of sending data out to third parties and giving them the opportunity to store it, opening up your database, and that's the way we've designed our databases to be opened up to third parties. But the access they get is limited to the data that they have access to, and they get special keys that allow them access to that data. So instead of sending it out to them, they have to come to the central store, the same place you come to see and store your data. They come to the same place to access the data. And again, it doesn't get decrypted until they receive the data. So it's encrypted at the point of origin and decrypted at the point of use, so that intermediaries cannot decrypt the data. And we help with the key management with all this situation to make it much easier. For those interested in key management, I probably won't have time today, but I'll put a video up online later or something for how key management can work in this situation. Another challenge is consent management for the users. So let's say you may have consent for a specific kind of data or for a specific type of analysis, but then new data becomes available that can be added to the analysis, or likewise a new analysis becomes available and you'd like to use that data. Typical kind of upfront, in paper, what have you, user consent are really not dynamic or flexible enough for the future we'd really like to see for mHealth. So we're trying to offer tools that provide user consent and transparency. For instance, a web portal where the user can go and see who'd like to see their data, for what purpose, who has already been granted access to their data, and how long are they using it? Can I set a timer? Can I revoke that data when I'm no longer comfortable with third parties using it? So really just giving them the control. And even in some cases, if it's of interest, we can even give them cryptographic keys to control the sharing of the data in a really, really foundational way. So the point here is that when the user's really bought in and can manage these data transparency issues, you can do more with the data because you have constant contact with that user to be able to get that consent. Okay, so that's kind of an overview of the pilot project, and I'll walk through an example of how it could be applied to mHealth. This is an age-in-place scenario that we think is fairly similar to probably many of the scenarios you're using, in the sense that, if I go back a slide, you're sensing data from multiple sources, you're analyzing it possibly in a central cloud location or even out at the edges, and you're trying to perform some kind of action or intervention on that data. So we have sensors in the home that can detect many aspects of a patient's life, an analysis engine that detects that an elderly patient may have fallen, and a notification that gets sent maybe to the patient, maybe to a neighbor or a caretaker to contact the patient to check on her. So fairly simple kind of scenario. There's several products out there today that try to do this, and many products that do a kind of similar sense, analyze, act thing. So how can we use the privacy as a foundation in this scenario to make it better? So one thing we'd like to propose doing early on is to segregate private information so that the way we've depicted this here is that red data is personally identifying information and blue data is not necessarily personally identifying information. It may be raw sensor data that gets relayed up to a central storage system via the phone. The user's GPS location is sensor data that is personally identifying because it says where they live most likely. So the idea here is we can actually encrypt these different pieces or types of data with completely different keys and then manage access to the data both logically so that when someone comes to access the data, they just don't get it if they don't have the right to access it. And also cryptographically. So even if someone did get access to the data when they shouldn't have, they need a key to decrypt the data, which they will not have the key. So the first step here is segregating that private information in a variety of ways. And our system tries to kind of do this foundationally. So when I say, how does this become a foundation for doing it? That's just the way data is stored in our system. Each piece of data or each type of data is stored with a different key to facilitate really fine-grained access control. So then when you process, you analyze the data. Let's say you have an analysis engine in the cloud or in a hub or somewhere that tries to understand whether a fall event has happened. In this case, they don't need to know who the user is to analyze this data. They don't need to know their GPS location or other information from sensors around the home, like how many times they've used the restroom today. All they need is the accelerometer data to determine whether or not they've fallen, for instance. So let's say you detect a fall with this engine. In order to get this data, it has its own special key that's only available to this software service. And so if an attacker attacks this software service, even if they get this key, all they can get is the sensor data that they have access to. They don't get any access to any other data. This is what attackers typically call escalation of privilege attacks. They attack one component in the system and then use that to escalate their privileges to other components in the system. So this type of segregation and cryptography improve that situation greatly. So then when the fall analysis engine detects the fall, they can write to the E3DB, possibly with a completely separate key that says a fall event has happened. What they can't do is unlock any identifying information, access sensors that aren't relevant to their work, or know about what interventions the fall analysis has indicated. So interventions are next. We can selectively recombine the data so that the intervention can be effective. But again, we don't need access to all the data. We just need the data that's relevant to the intervention. We need to know that a fall event has happened, but we don't need to know the accelerometer data. We don't need to know the restroom data, but we may need to know the GPS location and their relative or family member's mobile phone number, for instance. So again, this data can be segregated and selectively released to only the authorized parties so that they can take the appropriate action on the data. So here's a slide that tries to kind of combine the previous few pictures into a single kind of vision of this scenario where data comes in from multiple sources. An analysis happens based on these sources, and an event gets triggered for an intervention. And each one of these pieces of data is just stored in a way that it's separately encrypted, and so it can be separately shared and securely shared only to those components of the system that need access to the data. So a single flaw in any of the system doesn't cause all of the data to be leaked. If anything gets leaked, it's just the data that is accessible to that one system. Similarly, trying to depict here that other sensors don't get access to, data from the fitness band, or analysis engines don't see data from each other unless it's necessary. Other intervention systems don't see data from the intervention system unless it's necessary. So again, really trying to segregate the data. So I think that's probably where I'll just about wrap up. I have, again, a lot of detail if anybody is nerdy enough like me to care about the crypto systems, but I'll just wrap up with kind of a pitch to you saying we're looking for new projects that could benefit from this type of private sharing. We're very familiar with the proposal process with various government entities. So if you guys are looking for security help, we're happy to advise on the security story or help write those sections of those proposals as they come out if this type of thing seems beneficial to you. I'll also certainly offer, if you just want informal advice to run something by me, I'm always very happy to do so. For existing projects or something a little more short term, we are currently funded to run security and privacy pilots in this space. So if this product happens to sound useful, it may be possible to get you into our pilot and just have you as part of the team. So we're definitely looking for how can we have a positive impact on end users' lives and do the right thing with data. So I've put my contact information here again on this end slide. Feel free to send me a note. We will have a few minutes for questions here if you guys have any. And that scenario, I wrote it up and I put it up on our website for you. So if you want to kind of remind yourself, tozny.com/mHealth-privacy is where you can read up on the way we think about that, kind of the material I just presented, but it's a nice takeaway if that's of interest to you. So I think with that, I'll open the floor to any questions.